Hey guys, and welcome to the stream. It's a lovely day. We'll start out. Oof, this isn't scaled correctly. There we go. See, now we got a full screen now. We have a lovely stream today. I'm wearing the lovely cactus shirt. It's gonna be a wonderful day. I've got my lovely watch that I got for Christmas on. It's fantastic. I personally like it. Hello, is this Jordan Peterson podcast? Sure, why not? We can talk about why, as an academic, I do things very differently than Jordan Peterson does. Tell us to clean our rooms? Listen, guys. Do you think Einstein had to be told to clean his room? I don't think so. I don't think that Einstein ever had to be told to clean his room. At least after growing up, and guess what? He was plenty successful. Cleaning your room is not going to fix anything. That's not what's holding you back. Passed all my classes, 2 more classes next semester, and I have an electrical engineering degree. Hey, Freisig, that's pretty awesome. What classes do you have left to take? Listen, change of question. What's your favorite class that you took in your electrical engineering degree? You tell me yours, I'll tell you mine. Because I have an electrical engineering degree as well. I'm doing computer engineering now, but my undergrad is electrical. You also look kind of like Day 9. We're the same person. We're exactly the same. Except I have better shirts. See? I have a cactus shirt. I was going to... Advanced digital design was your favorite? I had a digital system design class. I really liked that as well. My favorite was a class I took on computer arithmetic, though. That was a lot of fun. Basically going into what modern CPUs use as far as arithmetic circuits. It's really interesting. It's a lot different than what you'd think. Brilliant EU stream. Yeah, man. Listen, we had a rough start this entire week trying to get EU streams. I have to walk 6 miles at like 3 a.m. Please button your shirt. Stop showing us so much chest. I really want to do computer engineering bad. Listen, it's never too late. In fact, what you learn in undergrad is not too, it's not too far from... Well, actually, I should say this. You're completely unqualified as a computer engineering student. You have a little more context, but even doing an undergrad in computer engineering, you're like completely unqualified. Nothing that you do is like something that's relevant anymore. Like even at a graduate class, in a graduate level, what you end up learning is stuff that was invented in like the 70s, right? So it's like 50 years old already. Yeah, I was only like 3 units or classes short of a computer engineering degree. Yeah, it's so close, the two. Like I wouldn't worry about having one or the other. Yeah, we're gonna have a lot of fun today. I'm writing micro benchmarks. I've been writing micro benchmarks. I need to change my username. I need to do one of two things. I either need to get my own desktop so that I don't have to worry about changing the name of my lab computer so that I don't reveal anything about myself. Or 2, no, I just need to get a desktop eventually. But I'm a poor grad student, so we're not going to do that. Actually, waiting to hear back from an FPGA developer graduate position still. Nice, where at? Or you don't have to tell me where at. I'll assume it's someplace cool. Okay. Okay, gotcha. There's a lot of really cool opportunities for that kind of work because not only is it relevant to computer engineering stuff, but high performance trading stuff. So financial places, they want to make those trades really, really quickly. So there's a lot of high performance computing that goes on in the financial sector as well. Oh, that's what they are? Okay. Yeah. No, yeah. There's a place called Citadel Securities in Chicago, and they released a very, very high frequency trading app. there's this place called Citadel Securities in Chicago, and they released something at GTC 2018, and it was a demystifying thing on Volta architecture, specifically for their application of high performance computing for low latency trading, but it ended up being really useful to us because that means we didn't have to reverse engineer their architecture, which was, hey, I'll take all the freedom from reverse engineering I can. Reverse engineering is, oof, it can be pretty messy. So we're going to talk a little bit about, what do I have open? I don't even know what I have open here. Oh, this is from this is Guri Sohi's paper. We're not going over this paper. I already went over this. Discard changes. Okay. So what we are doing today is I want to talk a little bit about micro benchmarking because a lot of people don't know what micro benchmarking is. I still have to go back a lot of old videos, been busy as of late. Hey, I've been busy too. In fact, this is the first time I've streamed since Monday. If any of you want to follow me on YouTube, the YouTube link's below. If you want to follow me on Twitter, the Twitter link's below. If you ever want to buy me a cup of coffee, I have the exact price of the coffee I get as a donation goal. So if you ever want to buy me a cup of coffee, including tax, it's exactly that price. And I know because I get it every day, or most days. We're also going to look at some tennis stuff later because I need to get a new tennis racket. You'll sub instead? Hey, if you want to sub, listen. Like I said, hey, thanks for the Twitch Prime sub. Listen, if you ever have a Twitch Prime sub that you need to get rid of, you're more than welcome to. But listen, where is the emote? We don't have any emotes yet. I'm already a poor grad student that doesn't have enough time to do his graduate work. Basically, if someone asks for mod, I just give them mod. Like, Raymond Zeta came over here and was just like, hey, can I have mod? And I said, sure, I'll mod you. I don't take this too seriously. Listen, if I ever make any money on this, hey, you're here. Nice. Look, it's the legendary mod of who solved the Riemann zeta function, who's getting ready to publish it. Isn't that right? Okay. So we're going to talk about micro. Yeah. Listen, he's gonna win the. He's got the Fields Medal lined up. He's got what else? What else does he have lined up? The Fields Medal. He'll get the Millennium Prize, which is like $1 million or something. Go down in textbooks everywhere. Abel Prize. Is that like better than the Fields Medal? I thought the Fields Medal was like the Nobel Prize in mathematics. What's the Abel Prize? No? What's the Fields Medal then? Listen, I don't know anything. All I know is that the Eckert and Mockley Award Field Medal is number 1. So what's the Abel Prize? Oh, okay, it's number 2. Listen, if you do the proof for the Riemann zeta function, I'm pretty sure you'll get the Fields Medal. Isn't that? Wait, did Andrew Wiles get the Fields Medal for? Oh, you get like all the medals. Okay. Did Andrew Wiles get it for the? What was it? I'm blanking. Nah, he was over 40. For Maslow's theorem. That's actually an interesting thing. Let's look up people that won the Fields Medal. Fields Medal recipients. Let's see if there's any. Probably not of people that I'm actually. How old are you? Don't have to answer. I'm 23 years old. That's how old I am. Okay. This is like way more comprehensive than for. This is so weird. Hey, you turned 23 3 weeks ago. Hey, congratulations, man. Happy birthday. This is way more comprehensive than the Eckert and Mockley Award. In the Eckert and Mockley Award, 90% of the people don't even have pages. How is this possible? The Eckert and Mockley Award is the highest award for computer engineering, and math, for some reason, has a better. Like, everyone has a. Oh yeah, Gregory Perlman. This was the Gregory Perlman. That was the guy that did the Poincare conjecture, right? That's that dude, right? Yep, that's who it is. Yep, that's what I thought. I recognize that face anywhere. Okay, so let's talk about micro benchmarking. So, what's the difference between a benchmark and a micro benchmark? So in a benchmark, we're trying to. So the first is a scope. So as far as the scope of a benchmark, we're trying to simulate something that's a real world scenario. And so this will be something like a benchmark like ray tracing. Some graphics thing, or maybe BFS, which is a breadth first search, or SSSP or something. So we're trying to simulate something that we would be doing in the real world. So, we generally use benchmarks when we're doing things like testing out an architecture. So if we do an architecture design and we go, okay, let's see how our system performs versus, the baseline. So if I make some change to the caches or change to the compute structure or change to whatever on, say, a Pascal Titan X graphics card, then I'll run it against all the same benchmarks that I have real data from the hardware, real hardware, not simulation, and I'll compare the two. Or I won't compare those two, but I'll correlate a model of the hardware that I have in the simulator, and then after I correlate that model, I will make my changes to the simulator, run it again, and then I'll just compare it against that baseline. But the entire idea is we're comparing it against, well, in the real world, these are the things we'd like to run. So it's not always the best comparison because we can't run a lot of the workloads that we'd like to because they're proprietary. So we can't simulate something like cuDNN. So NVIDIA's closed source machine learning libraries. We can't actually simulate that functionally on our simulator because it's written in their proprietary instruction set architecture. So our simulator works on the intermediate representation that is published, but they skipped the intermediate representation and they just wrote it in the low-level assembly. So we can't run that, but there's some benchmarks that we use to say close enough. So when we're talking about benchmarks, we're generally talking about something going on in the real world. So is it the ruler tool? Yeah. Okay. So what are we doing with micro benchmarks then? With micro benchmarks, we're looking at, one specific thing. So if we want to test something like memory system pressure, what we're doing there is we're just going to do an extraordinary amount of loads and stores in the hopes that we can exacerbate a problem. So if we want the worst case scenario, Or say we want to, you know, we want to test something like cache thrashing. So this is one of the things that this does. It allows us to, in a real world scenario, these might not be the common case, but it's still something that we have to keep in mind. We have to keep in mind what kind of fringe behaviors of applications are out there. So the entire system or the entire program, there might not be a ton of memory system pressure, but you might enter regions of code or certain scenarios where all of a sudden you have a ton of memory system pressure. And by memory system pressure, I mean tons of loads and stores that are all congesting the memory pipeline. So how we service loads and stores from main memory. Same thing with cache thrashing. The entire time we might get, we might have a pretty decent hit rate in the cache, but we might run into sequences where we're streaming, and so we're loading data that isn't reused. And so if we're loading data that isn't reused, then it's taking up space in the cache, and we're never going to hit on it. So we're going to run, or maybe our working set, the amount of data we're working with, is bigger than the size of the cache. And in that case, we're going to have cache thrashing because we can't fit all the data in the cache, and so by the time we maybe go around again and we try to access what we're looking at first, it's already been evicted. So we can use it to exacerbate these problems. That way we can see, worst case, how does our design do compared to real world? But it also does something else. So like we said, benchmarks, it's mainly just for simulating the real world. But it's still doing one specific thing, but another thing that it allows us to do is it allows us to test individual scenarios. And so what I mean by test individual scenarios is that it can help us do things like reverse engineering. So we can reverse engineer something like a modern graphics card fairly well. There's still a lot of work that needs to be done. But through micro benchmarking, we can get a pretty good idea of how a GPU architecture works. Sorry, I had to sneeze. And so what do we actually do here? So what do we mean by reverse engineering? How does that work? So we can step-by-step look at instructions and see the results after instructions. That way we can know, even though that the underlying ISA may not be published, we can still have an idea or even completely kind of know what those instructions do. Same thing with the instruction modifiers. What we do is we look at the source and assembly, which is what NVIDIA calls a proprietary instruction set architecture, also known as SAS, S-A-S-S. And what we do is we look at some benchmark or some micro benchmark, and we can step through the instructions one by one, and we can look at the registers before and after the instruction. And so by doing that, we can see, okay, what do the registers look like before? What do they look like afterwards? What was the data that was operated on? And then once we've done all that, we can go back and we can say, okay, in our simulator, what should we do when we run across this instruction? Then we can functionally execute the code. And this gets into the debate of should you have a simulator that functionally executes instructions, or should you have a trace-based? And there's pluses and minuses to both. The problem with a functional based, which is something that is more relevant to my lab now than ever, is that you have to reverse engineer the instruction set every hardware generation. That's a lot of work that is basically for zero publications. You can't publish a reverse engineering paper. No one cares. It's not novel. That would be like every single time someone comes up with a new formula for something, you have to reverse engineer, okay, what is integration? What is a derivative? What is addition? What is subtraction? None of those things by themselves need to be redefined. So you're not going to get published by saying what an integral is or what a derivative is. The same way that if you make a what's another good idea, or what's another thing? That's probably a good enough example. But the thing is, if you do that, if you functionally execute all the instructions, it means you can run arbitrary applications. So that means that if you have you can just compile any CUDA code and just run it on our simulator, and it runs. Now, the other option is to do what's called a trace-based simulator. And a trace-based simulator, you basically run an application on real hardware. You get a trace of the instructions before and after every single, before and after they execute, and you wind up with this big long trace. And so what we mean by trace is that you have 100% of the knowledge. You know how every branch is going to be resolved. You know the results of every single instruction. You know the results of every single load and store, every memory access. You know everything, whether it's a cache miss or a cache hit. You know. And so the benefit of this is that you don't have to functionally execute anything. You don't have to model the instruction set anymore. You have the results already. What's the problem with this? The problem is you can't run arbitrary applications. It means that with every application that you run, you have to first generate a trace of it. So it's a little less flexible in that regard. But sometimes that's a price you have to pay, especially if you're working with a proprietary instruction set. If you're working with a proprietary instruction set, there's nothing you can do. You're either stuck reverse engineering it or designing a trace-based simulator. And so we're at the point where reverse engineering it just takes too much effort. In the fall, I spent about 3 months reverse engineering the instruction set for Pascal, but Volta architecture is already out. So less than a year later, you already have to. Not all your work is lost. There is some subset of instructions it's the same, but there's still plenty of work to do. So let's get back to micro benchmarking though, and what micro benchmarking means. So we can test individual scenarios, which is useful for reverse engineering, which we just got on a tangent about. But what can you also do with micro benchmarking? You can use it for not just like reverse engineering to build a simulator, but also to try to do exploits. So sometimes we don't specifically care about whether or not we know exactly what the hardware is doing. Sometimes we'll never really know what it's doing. But we might be able to find scenarios where if we crash a program mid-execution, it might lead to some undefined state. What happens to everything there? So that's the case with something like Specter. So Specter did kind of something like that. Specter tried to lead you on this path of predict a branch, predict a branch, predict a branch, predict a branch. And then eventually, it would cause an exception, and it would crash the program. But you were already doing prediction, and you were kind of running ahead of your program. And so when you crashed, it didn't get rid of all this state and all these predictions. It left it in this weird kind of limbo type area where they weren't resolved. So they didn't do anything like squash the instructions or execute anything already, or they did execute, but they haven't been officially committed yet as executing correctly. But basically, they're still there. They're still present in something like memory, and so all of a sudden you can just access these things because they were predicted. You crashed it, technically they're not invalid. They're not something that we would just throw away because we don't know they technically exist because they're predictions. What I mean by that is the programmer shouldn't know that they exist because they're predictions. From the programmer side of things, everything happens in sequential order. You do instruction 1, then you do instruction 2, then you do instruction 3. At the other side of the hardware, you see instruction 1, instruction 2, instruction 3. Inside the hardware, it's you have no idea. There's no idea because there's instruction reordering, there's instruction reordering leading to out of order execution. There is out of order completion of instructions. So just because you executed instructions in some out of order fashion doesn't mean that they will even finish in that fashion. So, it's a wild scenario that you get into. But basically, what we can do is we can use micro benchmarks to test specific things. These very, what's a good word for that? The worst case scenarios where we're just causing an insane amount of cache thrashing. We can also use it to reverse engineer, and then we can also use it to see if there's any exploits, because we're just going to try to target specific sections of code. Okay, so what am I working on? What is Nick from Engineering Today working on? So we're working on a couple things, or I'm working on a couple things. I'm kind of the only person in my lab that's working on this, which is pretty neat because it means that I have full reign to explore whatever I want. That's why I got into academia, is because I wanted to do what I wanted to work on. That's what was fun to me. So I'm working on two things right now. One thing I just finished. The other thing I'm just starting. So one is leftover data in memory on the GPU. So what does this mean? This basically means that whenever you run something on the GPU, you first do something, you CUDA malloc, which is the same thing as malloc. You basically just allocate some memory. You do a CUDA memcopy, which says that you do a memory copy from this region of memory on the host, which is your PC, to the device, which is your graphics card. Then you launch your kernel, which is the program, the GPU program. GPU program runs, it does something, maybe it stores something to memory, does some computation, whatever, doesn't matter. And then it returns, and then you do a CUDA free, which is the same thing. You basically just release the memory and say, I don't want it anymore. And then your program exits. So the thing is, there's the question, okay, well, if I do something like that, and I recover, or if I do something like that and I allocate some memory on the GPU, what is in that memory before I load anything into it? Do I get values? Do I get zeros? Do I get garbage? What do I get? So there's a couple papers, and it turns out that there's some interesting observations. So if we look at Fermi and Kepler architecture cards, we get data. We get any data that we want. There's no cleaning that goes out. We can just recover arbitrary data. So if you load something into memory and your program exits, if I allocate the entire GPU's memory and I decide, okay, I just want to read the entire GPU memory, I don't want to write anything to memory, I just want to read it, we can 100% recover all of the data. However, Maxwell does something a little bit better. This is talking about Maxwell architecture. You get a segfault. So if you try to just read out the data, or so basically the scenario is, let's draw the scenario real quick. If you have process A and process B, this will be start, just do the straight lines. Let's use black and let's use a straight line. And then let's go, and let's use dark blue. No, let's use red to contrast black. So we're gonna start our program. Oh, whoops. That's why I wasn't drawing. So we're going to start both our applications. These are separate processes, remember. Here, process A will do a CUDA malloc, cmalloc, sorry. So we'll do a CUDA malloc. We'll do a memcopy to the GPU. We'll do a global store, and then we'll free. We'll free, it's CUDA free, but we're going to free the memory on the GPU. Now, after we free the memory on the GPU, this guy is going to do a CUDA malloc, but he's not going to memcopy anything over. He's just going to do a global load. So he's going to do a load without any previous store. Then he's going to do a memcopy. And then over here is just exit. They're both going to exit. So we have to do some synchronization between processes. I did that through shared memory. In the paper that I saw this from, they did it through Unix domain sockets, but it's just synchronization, so it doesn't matter. So what is our scenario here? So basically we copy some data over, we store it to global memory, then we just say, okay, I'm done, and I leave. This separate process that was started at the same time now allocates that memory. It doesn't write anything in that memory. It executes the same kernel to just copy something out of the GPU, and then it does a memory cop, or so it just copies it out, and then they both exit. So what is the scenario of what we're looking at here? We want to know what happens. So in Fermi and Kepler architecture, when we do this global load out, and we when we do this global load, we memcopy whatever we loaded out of the GPU to the CPU. This data right here is the same data from process A. So process A's data is just sitting there, and we can just take it all. Now granted, it would only be the ending data for that application, but we can still recover. If it's something like encryption, we can get stuff like private keys, right? Or we can get like final round keys. So that's bad for encryption. If your encryption process stops running on a GPU and you can copy out, the private key, pretty bad. Other applications, maybe it doesn't matter so much, but for some, it does. So we're saying that in Fermi and Kepler, this data you can completely read out. In Maxwell, you can memcopy it out, so it works up to here, but when you try to access this data, you get garbage, and it ends up causing a segfault if you try to print it. Now, it gets even better in Volta and Pascal. These are the two more modern architectures. You get zeros. So they do some cleanup. of the memory system. When they do that cleanup, I have no idea. Do they do it at kernel launch time? Do they do it at CUDA malloc time? Is it like I think cmalloc is supposed to give you zeros. So do they treat CUDA malloc like cmalloc, where it gives you a page of zeros, or it gives you however many bytes you've allocated and it will write those as zeros when you try to access it? Maybe. I'm not sure. And so this leads to an interesting discussion of, okay, well, can you do anything to maybe exploit this? And can you do anything to overcome these defenses? So here there's no defense. That's why I'm not including that in here. Here I can just read the data, so there's no defense. But is there a scenario where there are defenses that I can overcome? And so this leads to the question of, okay, what happens if I cause an exception and I crash the program? And this leads to the point of, where is this protection coming in at? If it's coming in at CUDA malloc time, then it doesn't matter if I crash, say, process A, because the zeroing comes in when I do something like CUDA malloc, maybe. The second thing is, okay, but maybe it's not. Maybe it happens at the termination. Maybe when a program exits gracefully or exits normally, when it finishes its kernel, maybe there's some cleanup functions that it runs and just says, okay, this person's done with this data, maybe at CUDA free time. So the first thing that we might want to know is, when does this zeroing happen? Does it happen when we free the data, or does it happen when we malloc the data? So that's something that we could discover using micro-benchmarks. So that's the first thing I've been working on. And so the initial answers I have is that Fermi and Kepler are awful security-wise, and you can read out arbitrary data. Maxwell gets a little bit better, but it's seg faults when you read the data. Volta and Pascal do the smart thing, and they zero the data. I shouldn't say the smart thing. Well, it's the smarter thing to do. The smarter thing would have been to zero the data all along, but there's some performance overhead, because you're going to have to waste time writing zeros, right? So it's not exactly like an obvious, okay, just write zero entire GPU memory. GPU has quite a bit of memory, and these are performance devices, so there is some overhead associated with that. But then again, there's also the security concerns. So that's one exploit. So what's the other thing I want to look at? So this is something I've already done. I did one. I'm working on two now, and we can see how you would go about writing that. I can't write in a terminal because it has revealing information. I haven't changed my username on my lab machine, and I don't want to. So maybe I'll have to do something. Okay, so what's the second thing? So the second thing is virtual address space isolation. So as you probably assumed, or maybe you haven't, we generally use virtual addresses. So we don't use physical addresses when we're accessing memory. Our virtual addresses go to something called a TLB, which is a translation lookaside buffer. We translate the virtual address to a physical address, and we access that physical part of memory. What does this allow us to do? It allows us to pretend that we have larger memory than we do. And what does it enable? It enables things like on-demand paging. So we can pretend that our memory system is huge, but not everything in that memory is stored in memory. Some of the stuff in that memory is stored on disk. But we can pretend that we have this giant memory space. So there's a big problem with this, or there's something that this also has to enable. It has to enable some kind of security. So what this means is that if we have two virtual address spaces, we don't want these virtual address spaces There's a chance that these virtual address spaces have the same address for two different processes. So we need to make sure that each process, even though it has its own individual virtual address space, we need to make sure that the translation of that address isn't to the same spot in memory if it's not allowed. Now, the way GPUs work, it's kind of naive, but there are some reasons for it. Basically, they partition the address space. They have some giant virtual address space, and they just partition it. You're not going to have overlapping mappings. You're just going to have your own set of mappings that you're given. So this leads to something, and that is two questions. So one, what happens? I'll just write out. What happens if we read another person's virtual address? And then two, what happens if we write another person's virtual address? This would be a pretty bad leak, because this isn't, hey, I left some lingering information on the GPU that, a lot of people won't know about. This is saying that while I'm running, somebody can read my memory. That can be a pretty bad thing. So how do we test this? So testing this is very similar to this initial scenario that we had up here. Except the thing is, what we have to do now, at CUDA malloc time, we get an address. We get an address of where in GPU memory we're going to be copying our data. So what we need to do, let's talk about our strategy. So one, what do we want to do? We want to pass addresses from process A to process B. Two, after we pass these addresses, we want to make sure we're running at the same time. So we have to sync up. We want to make sure that this is just kind of some boilerplate stuff. We want to make sure that one process doesn't exit early. So we have to have kernels that are long enough that that won't happen. And then after we pass these addresses, we want to try to dereference. We want to dereference these pointers, and we want to see, what do we get? So I already know what we get, because NVIDIA's documents say exactly what we get. It says that if you're using something that's pre-Volta architecture, you can just read and write any virtual address. Doesn't matter who it belongs to. It says you have complete access to any virtual address. Volta got a little bit smarter. It's still naive. Volta says, okay, well, you can still run, Volta says that you can still run and have these multiple processes. You can still read and write other people's data, but as soon as you do that, we're going to crash everything on the GPU. It says that we're going to cause a fatal exception. We're going to kill the entire GPU. So basically, they turned an information leakage attack into a denial of service attack. Now, get into the argument all you want about which one is better. From a security perspective, they're equally bad. Scenario one, someone reads my data. I don't want someone to read my data. Scenario two, I don't have access to the GPU. I'm also not happy. It's a subject. Which one is worse is kind of a null point. They're both bad enough. It's just, yeah, we're crashing this GPU with no survivors. That's what we're doing. And so that's the basic idea behind all of my research. It's that if let's look at these two scenarios. So the one scenario, actually, let's just pull up the NVIDIA white paper. NVIDIA MPS white paper. So let's look up out of range read. Here we go. So let's look at this for a second. So Volta MPS clients have a fully isolated GPU address space. Let's talk about pre-Volta. So this means Pascal, Maxwell, Fermi, Kepler. Really, we just care about Pascal and Maxwell. Those are considered modern. An out-of-range write in a CUDA kernel can modify CUDA accessible memory state of another process and will not trigger an error. So they're saying in their document that you can write someone else's process or read someone else's process, and nothing bad will happen. It won't tell you that someone did this. It won't say anything. You'll just do it. And not only can you read someone else's process while they're running, you can write it. So an out-of-range read, an out-of-range write will not trigger an error. An out-of-range read will not trigger an error. So this pre-Volta MPS behavior is constrained to memory accesses from pointers within CUDA kernels. So all this is saying is that any CUDA API restricts MPS clients from accessing any resources outside the MPS client's memory partition. This just says that we can't specifically do a mem copy of another process's memory, but we can be clever. Why do we care about security on the GPU? Because GPUs are becoming increasingly shared resources. So Volta GPUs have 80 SMs now. Pascal ones had 48. So they're becoming large enough where we can run multiple workloads on it. Second point. There are shared environments for GPUs that exist today. Think about a mobile phone. All the apps are untrusted. And we have a shared GPU. If we don't provide some kind of security on the GPU, do you want some other app on your phone to read out the frame buffer and read your banking information? And thirdly, think about all the WebGL exploits that are on the GPU. There's WebGL exploits that allows you to run arbitrary code on the CPU. And now granted that's through buggy drivers, but it's an exploit through the GPU. It's a GPU driver. So there's tons of motivations that we should care about security on the GPU. There isn't, it's growing now because people are starting, but you can make the same argument of why do we care about security on the CPU? And the answer is we don't care about either in reality. In reality, all the architectures in the past couple decades have been only focused on performance. But Hennessy and Patterson in their Turing, the Turing keynote at ISCA, which is considered one of the highest, if not the highest, computer architecture conferences, specifically said, yeah, we've only been carrying out performance. Sorry about that. Security is a big concern. So think about something like Specter, right? Or Meltdown. We took like a 30%, up to a 30% performance hit just for a security patch. That's insane. That's absolutely insane. So we should care about security on GPUs because, well, we don't want to have to keep patching and get rid of 30% and have 30% cuts in our performance all the time. If we can do it in a smart way and design something that isn't optimized solely for performance, and we optimize something that's intelligently designed for security from the ground up, then we won't have this 30% performance hit because security is one of our building blocks. Now, It's always a trade-off of best performance, best security. You can't get both. It's not possible. If you can, listen, do it, get your Eckert and Mockley Award, go for it. But it's not possible. No security thing has said, hey, we improved security and made it faster. If they did that, they said, here's our security thing that slowed it down, and then we sped it up with this performance thing. But that's why we should care. We should care because we use the cloud. And people have already found exploits in the cloud for CPU stuff. Why wouldn't they find exploits for GPU stuff? Where did the Specter patch cause a 30% performance hit? I don't know. I looked at benchmarks on it. I looked at benchmarks pre and post, and it caused up to 30%. I'm not saying everything was 30%, but it caused significant performance degradation. Specter Meltdown patch performance hit. Recent intel. I don't know if this is trustworthy. So before and after. So what is this? This is an arbitrary score. This isn't. Why don't they just show me graphs? So what did they show here? So older chips, of course, took a worse performance hit. So say in the 15% range instead of 6 to 8%. So a lot of modern GPUs looks like they got a 6 to 8%, but older ones got like a 15%. But that's depending on what application you're looking at, right? It's going to affect different things differently. Like the main thing was on branch prediction. So if you had a program that's branching a ton and their patch is on preventing you from branching a ton and speculative execution, then it's probably going to hurt you more than if you have something that's just computation based. Let's see. 30. No, there's some benchmarks that said 30%. That's why I said up to. I didn't say it was 30%. I said it was up to 30%. If there's only some place that decided to put a bunch of figures. Here's how and why. I know why it will. Okay. Specter. Graphs. Huh. Tom's Hardware. Here we go. Yeah, so I mean, the patches are going to get better, but the only way to patch it is hardware. Let's see. Tom's Hardware. Okay. So this is everything before and after patch. This is one workload. This is a 1.6x delta. Okay, so this is like frames per second. I mean, people don't want to take a 1% hit. If this is from 44.5 to what is this? What is it? Average min? Okay, so this is the minimum. Okay. Scroll down for ashes of singularity and click the third image. Is that the third image? These are the worst graphs I've ever seen. These are the least. This is why all these sites are awful. This is unintelligible graphs. This is the worst plotting I've ever seen. Okay, so it's min versus average. Okay, so average is 31.9. Min gets a little bit lower in each of them. I mean, looks like the rise. Oh, wait, where's the? Why don't they put these things side by side? Okay, I'm done looking at these. needless to say, we don't take... The patches get better, right? So patches get better over time because they make them more efficient. It's just like software. These are effectively software patches because you can't patch hardware. You can't change the silicon. This is a silicon problem. This isn't a software problem. Specter and Meltdown aren't problems with software, the way software was written. It's a problem with the silicon. And by problem with the silicon, I mean somebody found a way to exploit features that give us performance. So the things that give us performance are also things trying to get us. That's the key point here. A 30% probably was an early on thing. AMD/Ryzen is supposed to be unaffected. Unaffected from what? Unaffected from a performance hit or unaffected by Specter and Meltdown? Because there's no way it can be unaffected by Specter and Meltdown because it has out of order execution and it has speculative execution. And perf hit? Maybe. I doubt it. It doesn't seem possible. It doesn't seem possible that if you have the same problem that someone else has, somehow you're immune to the fix, unless they just didn't fix it well. I don't know. I'm skeptical on AMD stuff sometimes because AMD stuff, they don't have a ton of developers there. They have a good hardware team, or at least a decent hardware team. I don't know enough about them. I don't know. This is CPU stuff. I'm not a CPU architect. I know a fair bit about CPU architecture. If there was no perf hit, why were they doing speculative execution in the first place? Yeah, if they were getting an issue, there's an issue with speculative execution, you have to limit that. I mean, it's impossible not to get a perf hit. That's like saying in that case, then the original CPU could have been faster. If they did a patch and they got no perf hit, that means that they could have been doing something faster. Okay, but this is the key point here. So if we want to have shared GPUs, we can't have these security risks. And there are reasons why we want shared GPUs. GPUs are becoming large enough where we can fit multiple workloads on them. So it doesn't make sense for some training stuff, right? So training stuff, we want like, I don't know, 10 GPUs, right? We want multi-GPU systems. And they're all running one app. But for inference stuff, maybe we don't. Maybe they're small. Maybe they're small enough where we can run multiple on a single GPU. Or maybe we're running some other small apps, right? So then we're running multiple things on one GPU. But we can't do that right now. There's just not, the security guarantees aren't there. But I want them to be there. So that's what my research is. Okay. So let's see. What were we talking about? My G looks like a Y. Looks a little bit better. Okay. So the next benchmark that I have to write is for this virtual address space isolation. So that means we need to test to see if some other process can just read my memory. And so it says so in the docs that you can, but listen, never trust the docs. Just like if you're ever buying a hard drive and it says, oh, our mean time to failure is this, or our failure rate is this, don't believe it. They're lying to you. It's been proven. It's a published thing that those things aren't accurate, that those like 0.05% failure rate drives, that it's more like 4 to 5%. So yeah, don't believe it. If you want a source for that, here you go. They say it specifically in this book by Patterson and Hennessy, where they talk about doing this test on hundreds of thousands of drives, and that the failure rate is more like 5% than 0.05%, or whatever they claim. So if you're ever surprised, it's like, oh, my drive failed. It's like, I mean, they fail. Especially spinning disk drives. Listen, spinning disk drive, you have physical things moving. Physical things like to break. We want non-moving parts. Non-moving parts, good. Now, granted, there's still read-write. You have a read-write limit on things like Flash, right? And even things like memory. You have a read-write limit because it does wear out the memory cells. But get a new drive. It takes a while. Okay. So, what are we doing now? I haven't had a drive fail in years. I'm getting nervous that I'm going to lose all my pictures of cute anime girls. Huh. I haven't had a drive fail ever. I've never had a drive fail. I feel kind of lucky, but I've also... How do you interact with the GPU to write these benchmarks? CUDA or something? Yeah, they're all in CUDA. Let me see. Let me pull up. I have to be careful what I copy because it has some revealing info about myself on it. Okay. So this is what GPU code looks like, okay? So this is a simple CUDA kernel. This is from the first benchmark, right? So I do a global thread ID calculation. So these are intrinsic variables. These are predefined variables for each thread. They have an assigned block ID that's three-dimensional, X, Y, and Z. They have an assigned block dimension, X, Y, and Z. And then they have an assigned thread idea. I think just X and Y. Maybe Z. I think it's just X and Y, though. But you see, it's basically just C code. It's just C or C++. So this is the basic idea, is that you pass in pointers to these arrays. So int A, int B, int C, int D, and some int N. If it's just a variable, you don't have to pass a pointer to it. You can pass by value instead of by reference. Keep in mind that where these are pointing is GPU memory, not CPU memory. So when you do something like CUDA malloc, here, let me copy some more of the program. Okay. So here's later in the program. So these are just assigned up here as, let me copy these out too. So you just assign some pointers, and then you CUDA malloc, you pass the address of like DA, DB, DC, and DD. It's just common to do D in front to stand for device. That way you don't mix up host and device pointers. So CUDA malloc, you pass in this, which is technically of type void double star, so it's a pointer to a pointer. So that's why you're passing the address of D of A. And then you pass in how much you're allocating for this pointer. And then later on, you'll do something like, here we go. So you'll initialize, you'll have some other thing already initialized, and then eventually later in the program, you'll do a CUDA mem copy into device A from some pre-initialized vector. So this is the same size on the host. So you're basically copying whatever's in host memory here into device memory here, this size, and you specify CUDA mem copy host to device. Now there's also device to host to copy things out. Then you'll do something like launch your kernel, which if you ever want to see some weird syntax, here you go. So this is how you actually launch a kernel on the GPU. It looks like this. So it's the kernel name, which here is vector read write. It's these triple chevrons, so less than, less than, less than. Then you do grid size, block size. Oops. I don't know what it did. Huh. It's weird. There we go. So these are, I forgot what they call them, but these are three-dimensional things. So they're basically structs that have an X, Y, and Z component. So you can have a grid size that's three-dimensional. You can have a block size that's three-dimensional. If you just give it a value, a single value, like an int, so grid size, a block size just being an int, it will treat that as the other values are 0. So it'll treat it in this case as a one-dimensional array in memory, or a one-dimensional array of thread blocks. Then, just positionally, you put in your arguments. So device A, device B, device C, device D. So in this case, device C and device D are my outputs. Device A and device B are my inputs. And then n is just some int that's some constant that I need. And so I use, actually I don't need n in here. I forgot what, I used to, I could actually get rid of that. And so basically what I do is I copy the whatever's in A and B into C and D. So this is just a global store. So I'm storing a value to global memory. Then let's notice that I don't do any returns right here. So the return type is void. And that's because I'm not running on the CPU. I'm running on the GPU. So this doesn't execute like a normal function. So what I have to do after I execute is I have to copy back whatever I need. So I'll then call something like CUDA memcopy again, but this time device to host. So I'm copying from the GPU to the CPU. I'm copying into the host version of C, the device version of C. So I'm copying from the device to the host, and this many bytes. And then same thing here. I'm copying from the device to the host, this many bytes, and this says that I'm copying from the device to the host. These are predefined, right? So I didn't define CUDA memcopy device to host someplace. That's part of the language. That's a keyword in the language. And then that's it. And then of course, just like anything, you do something like CUDA free. Just like if you're a good boy and you decide to free your memory on the CPU, you should be a good boy and you should free your memory on the GPU as well. But that's pretty much how you interact with the GPU. So it's pretty straightforward. You write some kernel code, and so this global says it's a global function, and this global means that this is what's going to be run in the GPU. There's three different things. There's I forgot what the identifier. It's like global, local, and something else. One of them is a function that's callable by the CPU. The other one is a function that's callable from the CPU to the GPU. So in this case, this global says that the CPU code can call the GPU. But then there's another identifier that it's a function that the GPU can call on the GPU. So it's a function for the GPU, not a function for the CPU. And so it's a little bit different in that case. But I'm not a... So one thing to keep in mind is that I am not a software engineer, and I'm not a programmer. I'm an architect. I program as necessary. So if you see something and you don't like it, well, I say tough luck, because I'm not developing software, I'm developing hardware. I just happen to need to write software. But yeah, this is the basics of how you write something like a GPU program. Any questions from anyone? Anyone want to know anything else about how you write GPU code? Phantasm QB. Engineering Today is a Chad? I don't think I'm a Chad. What's a Chad? I don't know what you mean, buddy. Okay. So what else are we going to go over today? So that's the basics of how we write a CUDA program. It's not too hard. We see that it's pretty straightforward. I had some coffee this morning, so I'm feeling good today. Previously, my coffee was brought to you by Zlatan Best, our first donator to the stream. Near and dear to our hearts forever. Okay. So let's see. What's another interesting thing? So let's talk about, I guess, how GPUs work and how we program for GPUs, because we didn't really go over this section of it, right? We didn't go over grids and blocks. We can go over that a bit now. So let's make a new page. I forgot what a new page is. File, or no, it's page? Yeah, new page after. Okay. So let's talk about CUDA a little bit. Let's do a different color now. Let's do blue. So let's talk about, ew, that was bad. Okay. So how does CUDA work? So we're now moving from an environment on the CPU where most people, at least a lot of people, write single-threaded code, right? Maybe some of you people are, you're the brave guys. You're better. You're far better than I am, and you write all this super complicated multi-threaded applications on CPUs. I'm not that brave. I'm not that brave, and I don't want to be that brave. So this brings up an interesting point of, now we go from working with 6 threads, 8 threads. How do we work with 10,000 threads? How do we work with 100,000 threads? How do we work with 1,000,000 threads? Little bit different. Our problems seem to have scaled quite a bit. But we'll see that it's not actually it's not too hard. If you're new to the stream, I want to say thank you. Welcome again. If you want to join us any other time, you can go ahead and follow me. If you ever want to watch the videos that I post on YouTube, follow me there as well. And if you ever want to buy me a cup of coffee, go ahead. I won't stop you. I guarantee you I will buy coffee with it. Okay. I went to the farmer's market this morning. It was pretty good. They had a lot of good stuff. The Mennonites and Amish were out in force today with their baked goods. I always hate going to the farmer's market because there's like 2 tables always of like Mennonites and Amish. I don't know exactly what they are. Maybe they're Quakers or something. But there's always like 2 tables of Mennonites and Amish, and they're just covered in pies, and they're just covered in baked goods, and it's just, I want to buy all of them. They have like Dutch apple pie, which is so good. They have all these cakes, pastries, danishes, etc. I'll make myself hungry just thinking about it. Farmer's market's over now. Ends at noon. Okay. So let's talk about CUDA. So we have to think about what is the smallest granularity that we have to work with, or that we should be thinking about. So the smallest granularity that we have to think about is a thread. This is what's going to be executing these instructions line by line by line by line. It's important to note that in CUDA, or in GPUs, 2 points, instructions are issued in program order. However, they can finish out of order. So what does this mean? This means if I have something like a let's see, I have an add instruction followed by a memory instruction. So let's just say, oops, let's say I have an add followed by a load. So let's say the add takes 2 clock cycles. The load takes 10 clock cycles. So this says if I have a simple pipeline, if I have, it says if each of these are a clock cycle, it's going to look something like this. Let's see, 3, 4, 5, 6, 7, 8, 9, 10. The add may start the next clock cycle, but it's going to be done here. So this is going to be, say, what we call instruction commit, and we'll have an instruction commit here. So they're issued in order, but they're completing out of order. So 2 things that we should keep in mind when we're talking about GPU programming. Mort, how are you doing today? I hope you're having a wonderful Saturday. I had a lovely morning at the farmer's market, but we're here learning about CUDA right now. We talked a little bit about micro benchmarking earlier, but we should know a little bit about how to program the GPUs. So this is a key difference, though, between CPUs and GPUs, right? So CPUs are very different as they can issue out of program order, and they can finish out of program order. Here we have a little more, it's a little more rigid. We can still finish out of order, but now we have to at least issue in order. So what happens? Do we just have this giant pool of threads in the GPU that just execute? Well, turns out, no, of course not. That would be really, really difficult to manage if we just had a pool of threads. I can't even imagine what the hardware would look like. So what do? So we take this concept of a thread and we say, okay, well, let's put them together with some neighbors. And in the case of CUDA, let's put them with 31 other neighbors. And this is called a warp. So warps are collections of 32 threads. This is the lowest granularity that you can really think about. In AMD GPUs, a warp, I forget what they call a warp in AMD. It's a different word. In AMD's architecture, they're groups of 64 threads. They use a larger warp architecture. But with NVIDIA, they use groups of 32 threads in things called warps. So how do warps work? What happens is each thread has some built-in variables. So that has something like a block ID. It has a thread ID, and then it knows the grid dimension. And we'll go into what thread blocks are, and we'll go into what grids are in a little bit. But basically, we can use this thread ID to say, okay, which thread am I? Am I this thread? Am I this thread? We can use these intrinsic variables to determine who you are when you're executing. And these are built into every single thread. This is a thread level private variable. So each thread knows exactly who it is and exactly where it is, positionally in terms of the entire launch structure. So now that we have this concept of what a warp is, it's important to know that we don't program on the granularity of warps. This is just the lowest level that our hardware resources work. So when we're executing something, when we're executing code, we execute things at the level of a warp. And so this means that all 32 threads, let's go back to blue. This means that all 32 threads execute the same instruction in lock step. So what does that mean? That means that if we had an add followed by a load, that means all 32 threads do an add, and then all 32 threads do a load. Now, you may be thinking to yourself, does that mean I can only do things at the granularity? It has to be a multiple of 32? Well, turns out they were smart enough to think about this, which, is unsurprising. You're not going to have something that's perfectly a power of 2 or perfectly a multiple of 32. So how do you get around this? And so there's something called the active mask. So what's an active mask? The active mask says if I have 32 bits, say from 0 to 32, I can basically mask off and say, okay, well, these are 1, maybe this one is 1, and I'll only execute this instruction on these threads. So this allows me for my instructions to not do different things at the same time, but to either do the instruction or not do the instruction. So that's how we handle this kind of divergence, so this flow divergence. So we don't have to all do the add, but we can't do different things, but we can choose to do an instruction or not do an instruction. And that's what this active mask is. And a lot of times this is all grouped together in something that's called the SIMT stack. But the active mask is basically this lowest level granularity. But the key point is, for every single warp, at each instruction, all 32 threads are theoretically doing that instruction at the same time. So at the add, all 32 threads of that warp are doing an add. At the load, all 32 threads are doing a load. And there's clever things we can do on loads where we can coalesce them. And what do we mean by that? That means that if we're doing loads and it's all to, a contiguous region of memory, we can do one big load instead of 32 small loads. So we can save a little bit on our memory system pressure there. It makes it a little more complicated when we get to divergent axes. So if every thread wants to load from a different spot of memory, well, we can't coalesce those because they're not contiguous. But there's some ways to get around that too, and it's usually with something like prefetching, or maybe laying out your data cleverly. Okay. So let's go back to talking about the architecture. So we got to this point where we have all these different threads that are in a warp. Now, I already said that we don't program on the granularity of warps. That's just what it gets translated into. So what do we program on the granularity of? So it turns out what happens, I'll use a ruler so I don't make a mockery of myself. Turns out we have a little bit different of a structure. I think I did a decent box there, which I guess considering I have a straight edge isn't that impressive. So they actually execute on the level of something called a thread block. Let's do red. So this is I need to take the ruler off. So this is a thread block. Now, a thread block is made up of warps. So over here, you'll have a warp might have, that has 32 threads. They always have 32 threads. Warps always have 32 threads. Keep it in your head. Warps always have 32 threads. How many threads do warps have? 32. But a block has a bit higher of a limit. It has a lot higher of a limit in actuality. I don't know how that happened. Spooky. So a warp says, okay, well, got a notification on my phone. Okay. So this says I can launch things here, and I can have this multi-dimensional thing where all of a sudden I'm packing all these warps into something called a thread block. And remember, warps know where they are relative to a thread block. They know where they are relative to the grid. And what you basically have, oops, I forgot I deleted the T. So all of these, I need a new page, don't I? I'll stay here for a second. So all of these thread blocks get combined together and they get stacked on top of each other, and you wind up with this three-dimensional grid of blocks. So if we go back here, our block ID has an X. How did it turn pink? Our block ID has an X, Y, or Z component. And our grid dim has an X, Y, or Z component. And thread ID has an X and a Y, and I think also a Z component. And so what this says is that we can use grid dim to say, okay, how many blocks do I have going in each direction? In the X direction, in the Y direction, and then maybe in the Z direction. That's what grid dim says. Block dim says which one. If I have two blocks in the Z direction, this says that my block dim dot X is equal to 1. My block dim dot Y is equal to 1. And my block dim dot Z, if I'm talking about this one, will be 2. Or if I'm talking about this one, it'll be 1. So now I'm selecting which block that I'm working in. Let me get another page. Page. After, yeah. Okay. So let's draw that figure again. So let's draw a couple blocks. Let's draw them. That one's not very good. Let's draw one more. Okay. So in this case, if we consider this the X direction, and we consider this the Y direction, and we consider this the Z direction, let's consider block dim again. So block dim let's consider grid dim. So let's talk about grid dim first. So dot X, we have 3 in the X direction, so it'll be 3. In the Y direction, it'll be 1. We only have 1 in the Y direction. And in the Z direction, we'll only have 1 as well, because we only have a single block going up in the Z direction. Our, not block dim, block ID. So our block ID X, that will either be 1 or 2 or 3. So that's going to belong to 1, 2, or 3. And the other two are going to be constants. So dot y dot x. You starts with 0? Sure. And if you want to start with 0. Grid dim. Oh yeah, grid dim has to start with yeah. Grid dim is the one that has to start because it has to be a non-zero dimension. Otherwise you get zeros. Sure. So in this case, this will be 0, 1, 2, and then for dot xy, oops, these will both be 0. And that's because your block ID in both of these two directions, you just have a single block. But for X, you have these. And then you talk about thread ID. Which can be X, Y, or Z. I think it's X, Y, or Z. Thread ID CUDA. Is it three-dimensional? Thread indexing cheat sheet. This is a pretty good picture. Yeah. Yeah, it's three-dimensional. So it can be three-dimensional because we're accessing the threads that are now in this block. Remember, our lowest level of programming is at the block granularity, so that we have to be able to index every possible warp within that block. So we do that with the thread ID. So the grid dim tells us, okay, how big are we looking at this grid? In this, we have 3 blocks in the X direction, and we have a single block, which is just the size of this block in the Y, and a single block in the Z. So we really only care about the X direction here. So we're not even going to use the other two. For the block ID, that's saying, okay, well, I know that we're in the X direction, so I can ignore Y and Z for a second, because they're just constants. So my differentiating factor is which block is in the X direction. Is it block 0, is it block 1, or is it block 2? So then after I have that, I go, okay, which thread in the block am I looking at? So we lead to something along the lines of, if we're calculating a thread ID, so this is generally, if we're actually doing our global thread ID calculation, it's going to be very similar to what we saw earlier, or it's going to be exactly the same actually. So it's going to be block ID dot X times block dim dot X plus thread ID dot X. And so what is this doing here? So it's saying, okay, how many blocks are there? Or what is my block ID? So is it 0, is it 1, or is it 2? It's saying how big are these blocks in the X direction? Basically, how many threads are there in the X direction? So let's say that each of these blocks holds a single warp. So each block has a single warp. So we assign each block, each block has 32 threads, which is unlikely in many cases, but it can be the case. I mean, if you're just doing some example program. And for this, it is just to prove a point. So in this case, how does this look if we launch 3 blocks and then each block has a single warp of 32 threads? So in this case, let's break it down. So let's try to index, say, the first thread as you read. So what if we want to access the first thread of the second block? Let's see what this gives us. So our block ID will be 1. I'll just denote that as BID. Our block dim equals 32. Or, sorry, we'll do BDM. And then our thread ID, in this case, will be 0. So these are all intrinsic to that thread. So that thread is going to have a block ID of 1 times 32, because we're doing block ID times block dim, plus our thread ID 0. So this guy's going to have a global thread ID of 32. And we see that that makes sense because if we have warps that are 32 threads, and we have, you know, this big old line of threads, I'll make this picture bigger. We'll make this picture bigger, and we'll use a ruler. So if this is our global pool, what's going to happen? So from the programmer's point of view, we're mainly just thinking about it in terms of, I have this big pool of threads, right? Now, in terms of hardware, what do we think about? Well, now we're thinking about blocks. So we're going to say, okay, these have to be split at some granularity. And so what we end up doing is that if this is our X dimension, so if this is the X dimension, this guy will belong to the first block. So thread block 0. This guy will belong to thread block 1, and this guy will belong to thread block 2. Now, if we're looking at the thread ID for each of these blocks, the thread ID will start at 0, and then the last guy will have a thread ID of 31, if we're considering a single warp. Moogle fam, thanks for the 50-bit donation. I really appreciate it. I think that's like, what, 50 cents? Hey, that's on the way to getting a cup of coffee. That's pretty awesome. So if we're talking in terms of thread ID, every single one of these will be 0 to 31 if we have a single warp in these thread blocks. So 0 to 31, 0 to 31, 0 to 31. So now let's look at block ID. Block ID says, okay, well, this will be 0, this will be 1, and this will be 2. And then block dim, that will say, okay, well, there's 32 threads in each thread block. So this will be 32, this will be 32, and this will be 32. So that's how we wind up with this calculation of how to get what our global thread ID will be. Because in actuality, what we want to have is 0 over here. We want the first of this, so here's our last of the first thread block. We want to pretend like the next thing we're in thread block 2, or thread block 1 rather, our second thread block though, we want this thread to pretend like it's 32. And we want him to go 32 to 63. And we want the next guy to pretend that his thread ID is 64 all the way to 95, right? 32, 64, 96, yeah. So how does this work? And so that's how we get this calculation. That's what this calculation up here does in one dimension. This idea of block ID times block dim times thread ID. So if we do block ID times block dim times thread ID, we can get this form. Every thread will now have this exact value, or this variable TID. Will now have the exact value of the thread that we're expecting. So it'll have 0 here, it'll have 31 here, it'll have 32 here, not 0. It'll have 63 here, not 31. It'll have 95 here, not 31. It gets a little more complicated when you start doing three-dimensional, because then you have to worry about a three-dimensional grid. It's not just this linear array. So it makes it a little more complicated, but it's not that much more complicated. The ideas are pretty much the same. Basically what you end up doing is you start doing things by a row column basis. So instead of having just a linear array where you just index that, you now have to do a row column, and then for a two-dimensional thread block, for a two-dimensional grid. For a three-dimensional grid, it gets a little more complicated, and you end up having to do row, column, and then some depth. So you end up having to calculate three things, but the idea is exactly the same. You're just accessing a two-dimensional grid, or a three-dimensional grid, or in this case, a one-dimensional vector. But this is the basics of CUDA programming right here. So we can think of each thread as a normal CPU program. So each thread, if we had some CUDA code, let's make another page. New page after. So if we have some CUDA code, that's something like, okay, Pixel Shroom, what are we learning today? We're learning a little bit about GPU programming today. I got kind of distracted talking about benchmarking, and so we started doing some CUDA programming. We started out by talking about my research, but now we're doing something that's more general to everyone. And I realized that a lot of my figures are actually fairly decent. Maybe I should be a professor. Okay, so let's see. So what does CUDA code actually look like? So it always starts with an identifier, global. Is it lowercase? And then it's just void, and then some function name, some arguments, right? Nothing fancy there. So then we'll do our thread ID calculation. And like we said, that's going to be block dim times block ID plus thread ID. And this will be .x, 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 because we're only working the x dimension in this simple case. And then maybe we'll do something like, maybe we'll pass in, let's see, int star a. And then maybe our output will be int, let's do vector add. Int star a, int star b, int star c. Okay. So let's pretend like we have the case up here where we're launching three thread blocks, 96 total elements here. And let's pretend that each of these arrays are 96, they're arrays of 96 ints. So what can we do here? So we calculate our thread ID, and let's say we want to do vector add. So it's pretty simple. I'll do A, or let's say I'll do C of my thread ID is equal to A of my thread ID plus B of my thread ID. And that's it. we just did vector add. That's it. That's vector add on a GPU. Now, this is, of course, assuming that you're launching exactly as many threads as you have as your data is sized. So it's assuming that your data is a multiple of 32, right? But this is vector add. So we rely on this thread ID calculation to say, okay, so let's talk about thread 0. Let's talk about thread equals 32. Let's talk about thread equals 57. So for thread 0, our TID is going to be equal to 0. It will be C of 0 is equal to A of 0 plus B of 0. For this guy, our thread ID will be equal to 32. It will be C of 32 is equal to A of 32 plus B of 32. And then for 57, our TID is equal to 57. It's going to be C of 57 is equal to A of 57 plus B of 57. So that's the basic idea. So all of these things, we can assume that all the threads, so 0 through 31, are all doing this exact operation at the same time. And this happens on what's called an SM, or a streaming multiprocessor. And so basically, we assign, so this is a good conversation to have now. So how does this get assigned? So the first thing we do is we have to break down the architecture a little bit. So we have these things called SMs. So this will be SM, this will be an SM, and this will be an SM. Now when we launch a kernel, we end up assigning work at the granularity of thread blocks. So if we have 3 thread blocks that we're launching, it does this thing called round robin scheduling. And so we'll start assigning thread blocks to these SMs in a round robin fashion. Not necessarily in order like this, but it'll spread it out pretty evenly. So in this case, we'll have maybe thread block 0 here. Just for simplicity, we'll say we'll have thread block 1 here, and we'll have thread block 2 here. Now, on each SM, we go with the lower granularity. So for each SM, we then assign, from each thread block, we assign a warp. And we assign these warps, and I think a round robin fashion as well, or a loose round robin fashion. So basically, we first assign thread blocks. Thread blocks can have many warps on them, but we tie a thread block to an SM. Then on the SM, there's another scheduler that says, okay, start scheduling your warps. And then those get assigned. So in reality here, if we were to run this on a real system, and maybe I'll write this up after I take a break and maybe get some lunch in a bit, and then come back and we can actually profile it and we can see what's going on to some extent. You can't see the entire granularity, but you can get some idea. But this is the basic idea, where you have thread blocks. They get assigned to streaming multiprocessors on your GPU. Then once they're assigned to streaming multiprocessors through some scheduler, there's another scheduler that takes care of, okay, every thread block has some warps, start assigning warps to run. So in reality, threads 0 through 31 might be executing on this SM. Threads 32 through 63 might be executing on this SM. And threads 64 through 95 will be executing on this SM. And they could be executing concurrently. Now, you shouldn't rely on synchronization between thread blocks, but they are occurring in parallel somewhat. Okay. So that's the basic idea. So this calculation right here, I'm glad I put it this way. So this guy will be going on this SM. This guy will be going on this SM. And then this guy, no, that's still going on that SM, isn't it? So in this case, this guy is still going on this SM. And then if we had some other case, such as like t equals 72, that guy would be going on this SM. And that's the basic idea of GPU programming. So we split our work into manageable chunks. Then we have to decide, okay, how do we divide this into... We have to know about, first of all, warps, because we have to realize that we have to do things typically at the granularity of 32, because that's what's really being executed. So if we really want to tune our code, we have to be thinking in terms of warps. On top of warps, we have to think of how do we do this in terms of thread blocks. And then other than thread blocks, we have to think how do we structure this as a grid? How do we map our data to this grid? So that's the biggest thing. And that's why GPUs are so good with things like matrix multiplication and vector addition. It's because linear algebra maps really, really well to grids. And so that's how we get super high performance, and the programmability is not that hard, is because, you know, a matrix looks pretty much the same, and we can think about it computationally as the same on both the GPU and on the if we were to just do it on paper. Any questions on GPU stuff, intro GPU stuff? We'll do a little bit of questions for the next 7 minutes or so, or I might explain a little something else. And then I've been streaming for about 2 hours now, and I'm starving because it's already like 2 o'clock here. Seems good. Yeah, so this is the basics of GPU programming. But can anyone, do all of you notice the difference though between GPU programming and CPU programming? CPU programming, you don't have to know anything about the architecture. You have to know many things about the architecture for GPU programming. So what's another key point? So let's talk about one more key point. So global memory. It's slow, but you can access it anywhere. Let's talk about shared memory. Shared memory is fast. Shared memory is really fast. You can only access it per thread block. Shared memory has to be done at the thread block granularity. So we have an interesting optimization point here. So not only, so let's look at key difficulties. Let's talk about why people don't program GPUs. So one, we have to map our data to these, or not to these, let's say to this programmer's model. But not only do we have to map our data to this programmer's model, and so find a way to structure our data so it looks like a grid, we talk about optimization. So we have to further map our data to limited resources, i.e. shared memory. So we've already discussed that it can be it can be difficult to map data into this idea of a grid. But now if we want to make it fast, now we have to make sure that a thread block is only going to be using information that's private only to that thread block in shared memory. Because shared memory is at the SM level. Shared memory can't be accessed anywhere. You have to be within the same thread block. So this idea of splitting your workup into thread blocks just became way more complicated. And perhaps is a discussion for another time. But it's some interesting things to think about of why CPU programming is a lot easier compared to GPU programming. In CPU programming, I hate to say it, but you can be lazy sometimes. You don't have to know what the underlying x86 architecture is doing. In fact, if you did, you probably would never program anything, because you would just spend your entire life trying to wrap your head around out-of-order execution and trying to rationalize that in terms of optimizing your program rather than just writing your program and accepting that it works. The problem with GPUs is that you can't do that. GPUs are fundamentally a more simple architecture, but on two sides of the same coin, it's a fundamentally simple architecture, but they require you to know that architecture. The programming requires you to know that. You have to manually manage memory. It doesn't do it for you. So it's a little more difficult. Okay, any questions? Any final questions or things you want to know when we maybe return from lunch or maybe go over today? I needed to stream today. It's been far too long since I streamed last, so I wanted to do something fairly interesting. In a course I attended, we had to write CUDA code with shared memory, and it was a pain. At my first try, I was trying to put everything in SM, and of course it didn't fit. Yeah, so the thing is with, I think with, in terms of Volta architecture, you have 96K of shared memory. I think you only have 96K maximum available shared memory to use. Keep in mind that when you're programming, you also have the ability to determine whether or not you cache things or not. Isn't that interesting? Isn't that interesting? You can turn caches on or off. Now, whether they turn on or off is another story entirely. Sometimes they don't. Sometimes they say don't use the cache and it'll still use the cache. However, they say you can. How viable is it to try and guarantee that things are executed in groups of 32 of the same operation? Is it viable optimization or is it too hard? Brilliant, what do you mean by that? So how viable is it to try and guarantee that things are executed in groups of 32? So things are executed in groups of 32. The warp size is 32, so 32 has to execute. You basically have 32 lanes get executed at the same time on a warp. So it will always execute. Now there's an active mask up here that basically turns on or off the lanes. So it will always execute in terms of units of 32. However, there's no guarantee that two warps will execute concurrently or across SMs. There's no guarantee of the timing of that. So if you mean groups of 32 as far as the lanes are wasted if you don't have 32 correct. So yeah. So that's part of the optimization. So when I said that you have to map your data to this programmer's model, that's part of the optimization that you have to know. You have to know that the lowest granularity is 32. So if you start launching, let's say you launch, let's see. So if you have 48 SMs, no, let's see. Because you get a multiple thread blocks on one SM. So let's say you have, well, it's simple. So let's say you have 10 thread blocks, and then every single thread block, here, I'm going to switch camera because I don't need to explain anymore. Okay, so let's take it this scenario. So you have 10 thread blocks, each of which has 16 threads in it. So each of those thread blocks will be assigned to a different SM because it's round robin scheduling. It does a good job. It won't overlap thread blocks that on the same SM if there's open SMs. So now you have on 10 SMs, you have a warp with half the lanes off running. So essentially, you're spreading your data across 10 SMs when in reality you could be executing a full warp on 5 SMs. So that's part of this mapping thing, right? That's part of the mapping of your data to these structures. And it's really hard to get like 100% utilization. Nobody gets 100% utilization. You try your best, especially if you have data of different sizes. And you're not going to get uniform data that's just magically fits, right? So you have to build in, I didn't show it here in this simple CUDA kernel, but generally you want to do some checks here. That way you can get an arbitrary sized matrix in, and so you check an out of bounds. So if it's out of bounds, that thread will do nothing. You just say, there'll be like an if statement here, and it'll be like if TID is less than in, right? Less than the maximum number of threads that you have, then you execute that vector add. Otherwise, you do nothing. You just continue on. And inside the GPU, it'll make that active mask for you. Because that's based on control flow. That control flow is done for you by the SIMT stack. I think you define the block size, but I don't know if that's something virtual or real. The block size is real. So that's what's getting assigned to an SM. When you to the SMs here, you're assigning thread blocks. That's something that's real. The work that you're assigning, you assign it first to the SMs at the granularity of a thread block. Then once that thread block has been assigned to an SM, the warps are assigned for, oh, I answered you already. Yeah. Okay. Yep. Any other questions? Any final questions before? Here's a question. What should I get for lunch today? I'm hungry. I get Lebanese food all the time, but it's so good. It's hard not to just get it because it's just so good. Okay. So what do we want to do when we get back? When we get back from lunch? Probably be like an hour or two. Probably like an hour. Yeah, Lebanese. Vitality. Hey, thanks for joining us. We just went over some GPU programming and some stuff on micro benchmarking. And I'm actually very excited, and I think that my notes look halfway decent. My notes look better than half the professor's notes that I've seen write notes. So what do we want to do when we get back? What do we want to do? Are you in an office? I'm in my lab. This is the lab that I work in. I stream from my lab because I don't have a desktop. If you guys want to donate and get me a desktop, you're more than welcome to. But I only have a laptop, and I just remote in. And That's why I've had some trouble streaming recently, because it's not a complaint against my lab mates. They are just as this space is just as much theirs as it is mine, so I'm not going to kick them out of the lab just so I can stream. Yeah, it's pretty spacious. There are 1, 2, 3, 4, 5, 6. There's like 6 people that work in here. 4 from my, I think technically 7, but a couple people just remote in. There's like 7 people that work in here across 2 different professors. Students from 2 different professors, that is. Okay, so what? I think we'll probably get Lebanese. It's just too good. It's too good. If you guys haven't said hi to Beryllium yet, Beryllium is my first bits donator, I think. I think he donated like $5 in bits or something. Is that right? Something like that. So we'll probably get Lebanese. But what do we want to do when we get back? When we get back, what do we want to cover? So we covered the basics of CUDA programming. The problem is, it's hard. It's really, really hard for me to show an actual. Are you an IT guy? I'm a PhD student in computer architecture. So no, not really. I don't know any. I know very little about IT. Those are for other professionals other than myself. I know very little about IT. Are you an IT guy? I don't know. If you are, hey, that's cool. It's not my work. It is work. Turning it off and on again? Oh. Oh, come on. IT does more than turn things off and on. There's a lot of very interesting IT stuff. I used to work with, I did RAID, more on the business side. It's awful work. I don't think it can be awful, I can imagine. There's probably some redeeming factors, though. There's some cool stuff that you can probably do. Okay. So let's see. Okay, we've got a couple options, right? When we get back. 1, we can go over a paper. We can break down a research paper. 2, we can talk some more about GPU architecture, and we can talk about like the SIMT stack or something. 3, I don't know. I have no idea. We look at tennis rackets because I'm buying a tennis racket, and I need to shop for one. Those are the options. We'll probably do the 3rd one at the end anyway, just because I need to buy one. So what do we want to do when we get back? No languages. Have you ever tried Spanish? I took like 4 years of Spanish. I can understand it fairly well. Okay. I can understand pretty much all Spanish. Not all Spanish. I can understand a lot of Spanish. I have a hard time piecing it together. Korean or something would be cool. Yeah, probably. I think I already have it set up, so in 2 weekends or something, which I need to check because I might be in New Mexico. I might be in New Mexico then for a meeting. But there's somebody from Germany that is going to help me learn German. And those will be like 9 a.m. Eastern Standard Time, so like noonish GMT? Noon, 1? Or is it 2? It's 2 GMT. I'm in Eastern Time. Okay. Alright. So we're going to turn off the stream for a bit. Thanks, guys, for joining me. Do you have a language requirements for your PhD? What do you mean by language requirement? Are you talking about like a requirement that you know English, or a requirement of knowing another language? Second question, are you in the US or the EU for PhD? We had to learn 2 of 3, French, German, Russian. I have 0 language requirement for my PhD. There was none. I don't have to learn anything. I just need to know good old US of A English. There's no language requirement, no. I have, luckily they cut the requirements in my second to last year. That sounds like a waste of time. I hate saying that, but if you're a PhD student, you don't want to be taking classes, period, let alone classes that are orthogonal to your research. Now, correct me if I'm wrong on that, but that's my thoughts on it. And that's most people's thoughts on it, is that coursework is a waste of time. Like, it seems like a lot of older professors are really in this, math is a bit different. Yeah, well, I mean, what do you mean by math is a bit different? Are you talking about, like, seminars? Are you talking about, like, seminars on specific subjects and research in those areas? Or are you talking about, like, just courses that have books? Because, you know, courses are seminars for us. Yeah, that's the difference. So computer engineering, it's not. The research and the coursework side are very different. So, like, in an operating systems course, you'll learn classical operating systems theory, and that's nothing related to how the Linux kernel works. There might be a couple things here and there, but it's certainly not, you know, the most relevant or modern. Okay, so we're gonna get some lunch. Thanks for joining me. If you ever want to buy me coffee, feel free to donate. Like, if you want to do research in algebraic geometry, have a nice lunch. Thanks, Mort. I appreciate it. Like, if you want to do research in algebraic geometry, let's see, is computer engineering between computer science and electrical engineering? Kind of. You'll see that computer engineers at a PhD level, half the people are computer science majors, half the people are computer engineering majors. Basically, it's even if you have a thorough undergrad, you would need a bunch of coursework that's pretty sequential. Okay. Yeah, it's a lot different for computer engineering. For computer engineering, there's so many things that you can abstract away that you really just need to pick a point where you just cut it eventually. You just can't keep... So if every generation... So this is a common analogy that I do. So if 1980s, you have to learn this much to be a computer engineer. And 2016, you have to learn this much to be a computer engineer. So you have to cut it at some point, because it's just going to keep growing and growing and growing. And how are you supposed to ever become a computer engineer if you have to learn everything that came before you and then build on top of that every single time? Because that means 2030 comes around, you have to know this much. That's, you know, it doesn't make sense in computer engineering. It's a lot different in math, probably, but in computer engineering, that's the case. You have to abstract it away at a certain point, and you just have to say, these exist. We'll just take it as is, and then build on top of it. Okay, so we're going to have lunch now. Thanks for joining me. I'll see you guys in probably an hour or something. Yeah, and Matthew, you need to learn background. I'm not surprised.